In this video titled Electrostatics Part 3, we will be studying about the electric field due to point charge and dipole, etc. So before we actually study what is electric field, let's talk about the field concept. In physics, the forces in general are contact forces, requiring some sort of physical contact between the object on which the force is being applied as a push or a pull. However, in some situations we have action at a distance. The force is acting at a distance without any actual contact. For example, charges attract or repel each other without any contact. The gravitational force between Earth and the Moon is acting without any contact between the two heavenly bodies. Similarly, a magnet attracts an iron piece from a distance. In all such cases, we introduce the concept of the field. We say that charge A is in the electric field of charge B. Moon is in gravitational field of Earth. Iron piece is in magnetic field of the magnet. The electric field is defined as the space surrounding a charge. This is source charge which produces the field. Space around a charge in which it influences other charges. For example, if you keep a test charge here at point P, it will experience a repulsive force due to this source charge. We say that point P is in the field of the charge Q. In order to measure the strength of the field at point P, means how powerful, how strong the field is at P, we define a term electric field intensity, denoted by symbol E. For the purpose, we keep a small positive test charge Q naught at P. This charge must always be positive and should be vanishingly small. And find out the force on this charge. The force let us denote by F electric. Then electric field intensity at point P is defined as the force per unit small positive test charge placed at P. Remember, the test charge should be small so that it does not produce its own field. Otherwise, it will alter the field which it is supposed to measure. And it should always be positive so that we get the force in a particular direction. Now, electric field intensity is a vector quantity, and the direction of electric field intensity is same as that of the force on the positive charge. Means if source charge is positive, this charge will be repelled because test charge is always positive. So field is directed away from positive charge, and if the source charge happens to be negative, the force will be towards the charge and hence the field will be towards the charge. The SI unit of electric field intensity is Newton per Coulomb because it is force over charge. Dimensionally, we have E equal to force, that is mLT minus 2 divided by charge, which is current into time. So overall, the dimensions of electric field intensity happen to be mLT minus 3 ampere inverse. The concept can be used to solve a few problems. Question number 1. Calculate the electric field strength required to support the weight of a 1 milligram oil drop having plus 2e charge. Now in the problem, we have Q is equal to 2 electron charges equal to 2 into 1.6 into 10 to the power minus 19 coulomb. This 3.2 into 10 to the power minus 19 coulomb is then the charge. In order to support the weight, we need the force mg, that is weight of the oil drop, balanced by F electric. So this is the equation for equilibrium. F electric is QE and weight is mg, which gives you E equal to mg over q. So you can find the unknown strength of the field. Question number 2. A 40 milligram pendulum bob carrying 10 nanocoulomb charge is at rest in a uniform horizontal field of 20 kilonewton per coulomb. You have to calculate the tension and theta. The arrangement is shown in the diagram. You have a pendulum bob P at rest. The forces on the bob are its weight mg downward, the electric force F electric towards right or horizontal, and the tension T up the string. In order to solve this problem, you have to resolve T into two components. A component along vertical, that is T cos theta, and a component along horizontal, that is T sin theta. As the pendulum bob is in equilibrium, you have T cos theta balancing the weight mg and T sin theta balancing the electric force or QE. You can divide these two equations to get tangent theta equal to mg over QE, which gives you value of theta, and substituting value of theta, or you can square and add to get the value of the tension in the string. Continuing with the problems, let's take this question. Two charges plus 8 microcoulomb and minus 8 microcoulomb are placed at the vertices B and C of an equilateral triangle as shown. Calculate net field at point A. Now here we have two charges, 8 microcoulomb and minus 8 microcoulomb. To find net field at A, we have to take the superposition of the fields due to these two, that is vector sum of the field due to B and field due to C produced at point B. Field at A due to B, let's denote it by E1, equal to 1 over 4 pi epsilon naught QB, that is charge at B over AB square, which on substituting the values you get 72 into 10 to the power minus 3 Newton per coulomb. As the field is directed away from this positive charge, it will be along AP. Similarly, field at A due to charge at C, this is negative but same magnitude, same distance, therefore the field will again have the same intensity, 72 into 10 to the power minus 3 Newton per coulomb as in first case, but it will be directed towards this negative charge, that is along AQ. We denote this field by E2. So net field at A is vector sum of E1 and E2, which is given by E1 square plus E2 square plus 2 E1 E2 cosine of 120. This is parallelogram law of vector addition. As numerical values of E1 and E2 are same, you can take this as common, which leads you to 72 into 10 to the power minus 3, 1 plus 1 plus 2 into cos 120, which is minus half, giving you 72 into 10 to the power minus 3 Newton per coulomb. The direction of the resultant you can obtain by this formula tangent beta, where beta is angle found by the resultant with E2. The relation is tangent beta equal to E1 sin 120 over E1 plus E2 cos 120, leading you to this value root 3 on substitution, that is beta will come out to be 60 degrees. Now question number 3, 4 charges plus Q, minus Q and minus Q are placed at the corners of a square ABCD of each side root 2 meter as shown. Calculate the net field at point O, the intersection of the diagonals of the square. In order to find out, here is the hint. You have BD square, that is square of this diagonal, equal to AD square plus AB square, that is root 2 square plus root 2 square, or 2 plus 2 4, which gives you BD equal to 2 meter. We have OA equal to OB equal to OC equal to OD equal to half of BD, that is 1 meter. So at O we have 4 fields due to A directed away from this positive charge, that is along OC, and due to C again directed along OC because field is towards the negative charge. So field due to A is along OC, field due to C is again along OC. So these two fields we will add up. Similarly, for other two charges we will add up the fields away from B and towards D. Field due to A, let's call it EA. We can find out EOA equal to K Q over R square, where K is 1 over 4 pi epsilon naught. Since R, or the distance, happens to be 1 meter, so the field intensity comes out to be KQ. This is along OC as stated earlier. So net field at O due to A and that due to C will add up. All the 4 charges produce field of the same magnitude KQ. So we can add field due to A and that due to C, which will give you KQ plus KQ, 2KQ. Similarly, field due to B and D adds up, which gives you 2KQ along OD, 2KQ along OC and 2KQ along OD. These are perpendicular to each other, so you can get the net field by Pythagoras theorem. You can use Pythagoras theorem to add these fields, and the direction will be midway, that is it will bisect the angle between the diagonals, that is the angle DOC. The field will be perpendicularly downward from point O. Or the net field E is equal to 2KQ whole square plus 2KQ whole square equal to 2 root 2 KQ Newton per coulomb along OR, as shown in this diagram, where OR will be parallel to AD or BC.